Hi, I am Hossein Rafipour, and in this video I will introduce Whim, a new FSL tool for group-level analysis of diffusion MRI data. I will start by motivating the need for Whim, then explain the framework, and finally show some applications. Diffusion MRI is a powerful tool for studying the brain, especially the white matter. It measures how water molecules diffuse through tissue, and because water tends to move more easily along the axons than across them, we can use this signal to infer the orientation of the white matter fibers. From there, we can reconstruct the major wiring pathways of the brain and create these striking images of the white matter anatomy, giving us a unique view of the brain's structural connectivity. Tractography gives us impressive reconstructions of fiber pathways and show where connections are likely to be present. But it is not a direct quantitative measure of white matter integrity. The streamlines here are not showing the actual measurement of fiber strength. They simply indicate a probable presence of pathways reconstructed from diffusion signals. For instance, in this case, given the tractography results of two subjects, there is no direct, clear way to compare the fiber strengths of the white matter between these two subjects. One way to approach the problem of a cross-subject comparison of diffusion MRI data is implemented in tract-based spatial statistics, or TBSS. TBSS is based on the diffusion tensor model and uses measures such as fractional anisotropy as a proxy for white matter integrity. It creates a white matter skeleton using FA images that includes major fiber bundles in the deep white matter. Then it registers these skeletons to a common template space and projects FA values to these skeletons per subject. All of these steps are taken to ensure that the subject's data are highly aligned and we are comparing the same measurements across different subjects. And that's a key reason why TBSS has been so successful and widely used in the literature. Despite its success, TBSS has some important limitations. First, it is restricted to the white matter skeleton, which means much of the white matter is ignored. More importantly, it relies on the diffusion tensor model, which performs poorly in the regions with crossing fibers. For instance, FA values can be very low in the regions with crossing fibers, regardless of the strengths of each fiber population. And note that regions with crossing fibers make up a large portion of the white matter, including parts of the skeleton. This simple simulation illustrates the problem. Here, we model a voxel with two crossing fiber populations, where in both cases, one fiber population is degenerated. The only difference between the two scenarios is that the angle between the fibers is acute in the top case and is wide in the bottom one. Three voxel-wise metrics including mean signal, fractional isotropy, and mean diffusivity are shown at the bottom plots, where x-axis shows the degeneration process starting from 0 to 100% degeneration. The solid line and the dashed line show each of the scenarios explained at the top. In this case, FA is highly sensitive to the angle and produces different results, purely because of the geometry. The angle itself should not matter in this case, and the underlying biological change is identical. The other two measures show more consistent results between the two cases. This exposes a fundamental weakness of tensor-based measures in crossing fiber regions and show why explicitly modeling the individual fiber populations within a voxel is not just more informative, but it can be essential. So, we need to model the individual fiber populations within a voxel explicitly. The term that has been used for this is a fixel, short for fiber plus voxel, meaning a single fiber bundle element contained within a voxel. Thinking in terms of fixels allows us to move beyond voxel average measures like FA, and instead analyze fiber-specific properties, especially in complex regions with crossing fibers. A natural model for pixel-based analysis is the ball and sticks model. This model represents the diffusion data as the sum of a few compartments. A ball compartment that represents the signal from free water, and a few sticks that represent the signal from fiber bundles within each voxel, in other words, the pixels. As you have learned in the course, the ball and sticks model is widely used for probabilistic tractography, and it can be fitted using bedpost-X in FSL. Bedpost-X applies a Bayesian framework with MCMC sampling to estimate in each voxel the number of fiber populations and their orientations and signal fraction for each fiber population. Importantly, it provides the uncertainty estimates, which makes it a key tool for probabilistic tractography. One way to attempt a group comparison is to use the outputs of bedpost-X. For example, if we want to compare the fiber strengths across groups within a voxel, we can fit the model using bedpost-X, register the signal fractions to a common template space, and then try to match the pixels and compare them across groups. The difficulty is that there is a large inter-subject variability, both in the number of fibers within each voxel and also the orientations of each of them. It is often unclear how to establish a one-to-one correspondence between pixels across individuals. For instance, in this case, subject 1 might have only 2 fibers, whereas subject 2 might show 3 fibers, and subject 3 again 2 fibers. Also, if we just look at, like, for example, the red stick in the first subject, it is hard to assign it to either of the red or blue in both subject 2 and subject 3, as the orientations are very close. This is where Whim comes in. It uses a hierarchical framework in which we first define a group level distribution or a template space, and each subject's parameters are treated as samples taken from that distribution. By fitting all subjects simultaneously in this way, the parameters are consistent across subjects by construction, so there is no need for post-hoc matching. This approach avoids the correspondence problem that arises when subjects are fitted independently. For instance, in the previous example, where it was difficult to find a one-to-one mapping between the pixels post-hoc, if there is a template with a red and blue stick, each subject would have one red stick corresponding to red in the template and one blue stick corresponding to the blue in the template. So, by definition, there would be a one-to-one mapping across all subjects for pixels. This diagram shows how Whim builds the pixel template through an iterative process. We start by initializing subject parameters using a maximum likelihood. Next, we rotate each subject's orientation estimates into a common reference space. From these, we can update the group parameters, estimating the mean and variance across subjects per fiber orientation. We then rotate the group orientation estimates back into the original subject space and re-estimate the subject parameters, but this time using the group estimates as priors. This process is repeated iteratively until the model has converged, and then we repeat this for 1, 2, and 3 fiber populations per voxel. Once convergence is reached for all of them, we perform model selection within each voxel to determine the number of fiber populations, which would give us a pixel template. We used the pre-processed diffusion MRI data from 100 random subjects from the HCP Young Adult dataset and Oxford Multimodal Template OMM1 as the reference anatomical space for registration. This template specifies for each voxel the number of fiber populations presented in that voxel and the group mean and variance of the orientation per pixel. Each pixel in the template has a corresponding pixel in every subject, which creates a one-to-one mapping of pixels to the template and hence across subjects. This makes it possible to extract consistent fiber-specific metrics that are comparable across subjects. To demonstrate how Whim works and what is the main output, we applied it to a simple question. Does white matter fiber strength change with age in midlife? And if so, where in the brain does this occur? For this, we selected 400 random subjects from the UK Biobank dataset, aged between 45 and 65, balanced across sex. The pixel template was fitted to each subject individually to estimate fiber-specific parameters. We then used a general linear model with pixel signal fractions as independent variable and age as the main regressor, while controlling for sex and head size as covariates. This map shows the t-statistics from the GLM run on pixel signal fractions. Each pixel is shown in the voxel color-coded by the resulting t-statistics value versus age. The blue pixels highlight the fiber populations that become weaker with aging, whereas the red ones highlight those that become stronger. What's striking here is that in the magnified area, fibers running in the anterior-posterior direction show a different trend compared to those running through superior-inferior direction. This orientation-specific pattern is something voxel-wise metrics like FA cannot capture, since they collapse all the fiber population informations within a voxel into a single number. Once we have t-statistics for each pixel, the next step is to identify which changes are statistically significant. To do this, we would normally set a threshold on the t-values, but because we are testing thousands of pixels across the brain, some will cross that threshold purely by chance. This is why we need a correction for multiple comparison. In Whim, we use a modified version of threshold-free cluster enhancement, or TFCE, which you learned about in the fMRI analysis part of the course. The key difference is how we define a neighborhood here. Instead of relying only on the spatial proximity, we also take into account angular similarity between fibers. This way, pixels are grouped together not just if they are close in space, but also if they share a similar orientation. For instance, the green pixel in the center of the grid is considered to be neighbor with all the red ones, but not the gray ones. This form of neighborhood definition allows us to cluster the pixels within the same tract and avoid mixing the signals from different tracks present in the same voxel. After applying the threshold and correcting for multiple comparisons, we can filter out the non-significant changes and highlight only those that survive the threshold. What we see here is that only some of the negative trends remain significant and there is no significant positive change detected. In particular, a region of the corpus callosum shows a clear decline with aging. This fiber-specific analysis allowed us to detect a change that was specific to a single tract, which would have been difficult to detect with voxel-wise measures, especially in the crossing fiber regions. In the second application, we used an animal model where a unilateral injury was induced in the visual pathway of 5 rats. Because of the experimental setup, we can assume that a fiber-specific change has occurred in the affected pathways, and contralateral fibers must have not changed, particularly in optic chiasm where the two tracks cross. This makes this dataset a good validation test. If Whim works as intended, it should detect changes specifically in the injured fiber while leaving the other fiber population within the same voxel unchanged. The standard ball and sticks model assumes that diffusion within each pixel is entirely along the axons, with no radial component. Adding extra parameters to the model without any constraints may make the model fitting challenging. However, if we use the prior information on the fiber orientations provided by the pixel template, we are able to extend this model. Specifically, we add a radial diffusivity parameter for each pixel. This allows us to capture not only changes in the signal fractions, but also changes in perpendicular diffusivity for each fiber population separately. Here, we show the results from fitting the extended model with signal fractions per fiber on the left and perpendicular diffusivity on the right, averaged across all the voxels in the optic chiasm area. The first box plots are from the control group where there was no injury, and the next two shows the intact and injured fiber populations in the lesioned animals. Looking at the injured fibers in both plots, we see clear changes. Their signal fraction is decreased while the radial diffusivity is increased, which indicates a loss of axonal barriers in the damaged tract. This confirms that these measures are sensitive to the change of microstructure within each fiber. More importantly, the intact fibers in the lesioned animals overlap well with the control group. confirming that these estimates are fiber-specific and not mixed across fiber populations present in the same voxel. Whim is implemented as an FSL command line tool. It includes a set of subcommands that handle the main stages of the pipeline, from subject-level processing to group modeling and statistical analysis. In the next few slides, I will walk through these subcommands and show how they are used in practice. The first subcommand is Whim subject, which fits the model at the individual subject level. The input is the subject's diffusion MRI data together with transformation to a common anatomical space. It can also accept a pixel template. The output is the estimated fiber-specific parameters for that subject. The subject-level results are then used as input for the group-level analysis. For this step, we strongly recommend using a multi-model registration that includes diffusion data in the registration process, since conventional structural images do not provide sufficient contrast for accurate alignment of deep white matter. A good registration option within FSL is mmorph, which is well suited for this purpose. The next subcommand is Whim group. This takes the individual subject parameter estimates from the previous step and combines them to build a probabilistic pixel template. The template includes for each voxel the average orientation across subjects and the variance of each fiber orientation. This serves as the common reference for the group analysis. The next subcommand is Whim-em. This stage brings together the previous two steps and run them iteratively, fitting both the subject-level parameters and group-level parameters. It uses an expectation maximization framework, hence the name. To keep the process organized and reproducible, Whim-em uses the FSL file tree for more efficient file management, and it's integrated with FSL pipe to optimize the workflow and automate the processing across multiple subjects. The last subcommand for creating a template is Whim select, which does the model selection. It takes the group parameter estimates for 1, 2, and 3 number of fibers per voxel and then uses a criterion, either BIC, AIC, or log likelihood, and a predefined thresholds to decide on the number of fibers per voxel. The output is a full pixel template that for each voxel it includes the number of fibers and orientation estimates per pixel. Another subcommand is Whim metric, which extracts pixel-specific metrics from diffusion data for new subjects given a pixel template. This step is very similar to Whim subjects, but with one key difference. Instead of estimating parameters through the full model fitting for different number of fibers per voxel, it directly computes pixel level measures defined by the template, and it fits extended model to the data as well. This is useful when you already have a template and you directly want to derive fiber-specific metrics per subject. The last subcommand is Whim-glm, which performs the statistical analysis across subjects. It takes the subject-level extracted pixel metrics and applies a general linear model to test for group differences or regression with continuous variables. The output is a set of statistical maps, including t-statistics and corrected p-values, which can then be visualized and interpreted in FSLIs. In short, this table compares Whim with two of the most widely used FSL tools for diffusion modeling, TBSS and bedpost-X. TBSS allows for group comparisons, but it is restricted to the skeleton and based on tensor model, which cannot handle crossing fibers well. Bedpost-X, on the other hand, models crossing fibers in detail, and it's good for tractography, but it works only at the single subject level and does not provide a framework for group comparison. Whim combines the strengths of both. It models crossing fibers like bedpost-X while also enabling group comparisons across whole byte matter rather than just the skeleton. To summarize, Whim is a new FSL tool for group-level analysis of diffusion MRI data. It provides fiber-specific microstructural measures across the whole white matter, ready for group comparisons. Users can build study-specific templates or use the existing ones. Whim source code is available on GitLab. For more details about the method, you can also refer to the paper published in Imaging Neuroscience. Also, there is practical available as a part of FSL course.